All right, we are live. Okay, I'm all alone right now. And what I would like to do is share with you a revelation. Let me get a whiteboard. I'll share with you a revelation, my explanation to the famous double slit experiment. It's really rather simple, rather mechanical. So let me try. Let me see. Yeah, the paper moves. Let me move it to here. A little bit more. Center. Okay, like this. All right, let's talk about the let's start from the end. I'll explain the double slit experiment, and then I'll explain maybe the double slit experiment. No, I'll explain it. I'll explain, and then I'll come back and explain. I'll explain the solution. Let's talk about why isn't this widening properly? What's going on here? Create new. Why isn't it? I want it to be bigger. Okay, that's better. Okay, try this again. Uh, okay, let's move this here. So let's talk about the explanation to the double slit experiment. So, the solution is rather simple. So we know that a particle, let's assume, right? Let's assume what we've been taught about the double slit experiment. So we assume that we have, one second, we have some sort of a cannon, a nanoscopic, a quantum size, a very, very, very tiny cannon that fires very tiny particles, quantum particles. Let's say it's a photon or an electron or anything really, really tiny. Okay, but I think a photon would be the best. Right, so I'm assuming that there are photons, that Einstein was correct in his photoelectric effect, that that photons exist. So we're firing a photon. Okay, by the way, how do we fire a photon? That's not simple. So we can never, I don't think we can, I don't think when we fire the photon, we don't see the photon. All we assume is that light is emitted. But light, we know, is a wave. I mean, it's an electromagnetic wave. But Einstein said, yeah, but it's also a photon. So, and that's exactly what I'm going to talk about. This duality. Basically, I'm going to explain how you get duality in nature from first principles, and it's a mechanical explanation, somewhat mechanical. That's it. Okay, let's begin. So we have a light emitter. So somehow we are emitting light even with a candle. I think we can emit light even with a candle. Light comes out. We're assuming that light contains photons. So photons are in the light, and that's fine. And here we have our famous two slits. So we have here two slits. And here we have the board or whatever where we see the light, where we actually see the light. And what we discovered in the double slit, the quantum version of the double slit experiment, that we have a very low emitting of light, very low. I don't want to say frequency, but we're assuming that only one photon is coming out at a time, basically. So one photon comes out and it shows up here, another one shows up here, and another one shows up here. And sooner or later, what we're beginning to see, we're not seeing two, right? We would expect to see two slits or something, but no, what we end up seeing is a wave pattern, that there is high density of photons here, low density of photons here, high density, low density, high density. Basically, it's a wave pattern. So this is really weird because Einstein proved that the light is composed of photons. We know light is a wave, So we're already confused whether light is a photon or a wave, which is why certain people really got upset at the photo at Einstein's paper on the photoelectric effect. I was very upset about it. Einstein in his later years was very confused about it. I saw something that he wrote, so it's very confusing. So what's going on? How could light be both a particle and a wave? And then we discovered if we do the same thing with electrons, we get the same. So what the heck is going on? Because electrons, I mean, those you can basically see that electrons are particles because you see the lightning. Lightning is not a wave. Lightning, you see the particles when you touch the door in the winter and you get zapped. You see that spark. That's not a wave. Those appear to be actual particles, but they tell us that they fired electrons, and again they got this wave pattern. Very confusing. How could this be? So here's the explanation. The explanation is that the medium, right? There is a medium, even though this is in a so-called vacuum. So the word vacuum is incorrect. It's a misnomer. This is the beginning, the middle, and the end maybe of the problem. The problem is that we're saying that there is a vacuum, but actually there isn't a vacuum. We know there isn't a vacuum from many. I would say the best reason to suspect there isn't a vacuum is from general relativity, is from the theory of gravity. We know that, right? Newton said, how could there be action at a distance through a vacuum? That doesn't make any sense. That the Earth could pull the Moon through a vacuum. How could that be? That doesn't make any sense. So my conclusion is that, or Einstein's conclusion is that that space itself is somewhat rigid. It's a fabric. It's a three-dimensional fabric in which the Moon is embedded, and the Earth sucks in this volume of fabric. It keeps sucking it in, and it's pulling the Moon as the Moon is going around. But that is what is holding the Moon in place. It's this space that is a fabric that is it flowing through the Moon? To from the Earth point of view, yeah, it must be flowing through the Moon. From the Moon's point of view, I don't know, but it's still very confusing. This fabric is confusing, but it is a fabric. So okay, so it's a fabric, and that's how light as a wave travels, right? If it were truly a vacuum, if the vacuum was truly a vacuum, then how can a wave propagate through a vacuum? So, of course, space and what we call a vacuum cannot be a vacuum. It must be something actually extremely rigid. In order for a wave to travel through it at the speed of light, at 300 million meters per second, that's a million times faster than the speed of sound. So imagine that when I'm speaking right now, that sound travels at 300 meters per second approximately. So, and that's kind of rigid, right? Air is kind of rigid. It's not that rigid, it's a gas. But light travels a million times faster, 300 million times meters per second. So, because the speed of waves is determined by the medium, and the more densely packed the medium, right through water, the speed of sound is faster, and through a solid object, the speed of sound is even faster. So imagine a wave like sound. You could imagine that it's basically a sound wave traveling through a super solid, super condensed solid. It could reach the speed of light, the 300 million meters per second. So this vacuum is actually a very, very densely packed solid that for some reason we cannot, well, I'll get to it right away. For some reason we cannot feel this solid, but it's a solid, because otherwise how can waves travel through it at such an incredible speeds? Waves always travel through the space fabric at this incredible speed, whether it's electromagnetic waves or gravitational waves, and it's always the same speed. This proves again that it's this it's this fabric through which these waves propagate. Okay, so in the double slit experiment, there is no vacuum. I don't care about the air. As far as I'm concerned, there is a solid here. Now you're going to say, but wait a minute, what? So particles travel through a solid? The answer is, of course not. Of course, particles cannot travel through such a densely packed solid. So how can a particle reach the backside, the backboard, the detector board? How's my audio? I never checked my audio. I hope I'm streaming. Let me check 1 second. Let me open it up. Let me give me a minute to just make sure that the audio is good. Okay. Is it? It's kind of okay. It's good enough. All right. Let me just 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It's fine. Let me just put the link to YouTube here if anybody joins us, and let me put the link from here to YouTube. Here is YouTube. Let me put it here so anyone can join us. Is anybody with us? Is anybody? I don't think anybody's watching, which is fine. Anyway, so the question is, um, so how could a particle travel through a solid? Oh my God, what is going on? So how could a particle travel? Oh my God, what the heck? Okay, let me touch it and then move it. Okay. So how could a particle travel through a solid? So the answer is particles cannot travel through solids. All right. So Einstein said it is a particle. At one point, it's a particle. It looks like a wave. It's a wave dispersion, but it looks like a particle hit. So what's going on? So the answer is particles cannot move through space. Only waves can move through space. So as soon as we fire, maybe in the beginning it comes out as a particle, but in order to traverse space that is a solid fabric, a super dense solid fabric, the only way a particle can travel through it is as a wave. So it's converted into a wave. It of course travels as a wave, as a three-dimensional wave. It's a three-dimensional wave. It goes through the double slits as a wave, creates an interference pattern. All this time, it's completely a wave. And then when it stops moving, what we call it interacts with an observer, that interaction means it stopped moving. Once it stops moving, then it's again a particle. That's the story. Now the question is, how can it convert from a wave to a particle? What is this magic? So the answer is be right. Can anybody guess? It's really very straightforward. How can we convert particles to waves and waves to particles? What's going on? How could that be? You're either a wave or a particle. So the answer is no. E equals mc squared. We can readily convert a mass to energy. And the energy could be anything. It could be a wave. So the particle is allowed by E equals mc squared. A particle is allowed to be completely converted into a wave, travel as a wave through a completely super dense, super solid fabric, interact with whatever the universe has in its path as a wave, create the interference pattern that we know that waves create, and then at the end, when it interacts, it stops. When it stops, it doesn't need to move through the solid space object, and now it's converted readily with no contradiction back to mass. There's no problem. This is there's no energy loss in this conversion. And so if you're going to complain, how can you convert wave to a particle to wave and wave to particle? How can you do that? That's like, yeah, it's allowed. You should have complained the day Einstein said E equals mc squared. You should have complained back then. Don't complain now. Once you accepted that you can convert energy to mass and mass to energy so readily, then why are you surprised that it's possible to convert a particle to wave and wave to particle? It's completely fine. So, in my opinion, the intuition that you cannot move through space, particles cannot move through space, or whatever it is, right? Either as energy or mass, right? When it's moving, it's got to be a wave. When it's still, it's got to be a particle, because still things cannot be waves. A wave cannot be still, right? Intuitively. How can a wave be still? And how can the question is, how can a particle move? Well, it's a solid. If you assume this is a solid, a super dense solid, the likes of which we've never seen, this creates a wave that moves 1,000,000 times faster than sound. This is a super solid. So a particle readily converts by E equals mc squared into a wave. It replaces its energy, right? A particle is energy because E equals mc squared. It just gives away its mass, whatever that is, and becomes pure energy, a pure formation, a pure propagation of density. It's just a propagation of density across a medium, just like a water wave. You can now here comes the mechanical explanation. This is doable with any wave. Anytime you see surface waves in a right, when you drop the pebble, this comes from this experiment. You drop the pebble in the lake, in the pond, in the puddle, and you get these let's do a top view. So you drop a pebble and you get these waves coming out. These waves are energy. They're convertible into matter according to E equals mc squared. I don't know mechanically how to convert this back, but in nature, at the quantum level, this is already, at this point, I don't know the explanation. I'm just giving you one, I'm peeling the onion of lack of knowledge one layer at a time. I'm just giving you one layer of explanation. You can take it from here. And I'm not giving you any other experiment. I'm not talking about the other experiments. I haven't thought about any of the other. The wave particle duality coming out of this experiment, this is uh, this is one layer of explanation that I'm giving you right now. The rest of the experiments and exactly how it works, because this is a three-dimensional wave, it's going in every direction. But at the end, the energy is completely here, I think. I don't know. So there's a limit to the amount of peeling of the onion that I can do, the onion of science. I'm just giving you this one layer, the layer of the particle wave duality. So particle wave duality is completely allowed by E equals mc squared. Complain to whoever proved to you that E equals mc squared. Once you accept that energy and mass are interchangeable, then at the quantum level, I would say there's no energy loss in the process. Now, one of the things that comes out of this is that there is no motion through space, which is bizarre. Well, I didn't invent that motion through space is impossible as a particle. I didn't invent this new principle to explain this experiment. It actually came out from directly from general relativity. My intuition is that the space continuum, and by the way, don't say space time. There is no space time. There's only space. The space continuum is a solid in which the moon is embedded, and it cannot move out of there. I didn't look too deeply into what creates this intuition. Oh yeah, I have another proof. I'll show you the proof. But that's where it came from. Once it came out of there, then it became possible to explain, okay, so everything moves as a wave. Wait a minute. This can explain the particle wave duality. So my intuition was that it's a solid. So it's impossible to move. How can things move through a solid? Now, And then I said, okay, so it must be traveling as a wave. So every time we move through space, it must be as a wave. At least when we observe other people moving with respect to us, it must be as a wave. And that's why there is there's a speed limit. Why? Oh, somebody's here. Hey, Derek. That's why there is a speed limit in the universe for solid objects. How are you doing? So solid objects, we know that they're limited by the speed of light. Why are they limited by the speed of light? Why would a particle be limited by the speed of light? A particle is not a wave. A wave is determined, the speed of a wave is completely determined by the fabric, by the medium through which it moves. A water wave, a sound wave. When I'm speaking, the sound wave velocity, speed is completely determined by the medium, by the humidity, by the density, by the temperature. Yeah, it has nothing to do with my voice, with anything I do, with the amplitude, with the frequency. I cannot influence, as far as I know, I cannot influence the speed of the wave. All right, so why are objects not allowed to go faster? Which I don't know if objects are not allowed to go faster than light, but let's assume that Einstein proved that we cannot observe an object moving faster than light. Right? There is this speed limit. Um, we have anyway. Why did Einstein say? I need to figure out exactly why he said it. But let's assume it's true that we cannot observe objects moving faster than light. We cannot cause them to accelerate. What's really stopping it from moving faster than light? Why that? I mean, if a particle, it's a particle. How could a particle be blocked from moving at any? It should be able to move at any velocity that it wishes, unless ultimately it's a wave. And because it's a wave, it's limited by the medium. So when we observe a star or whatever, something moving through space, it cannot move. We cannot observe it moving faster than waves in the medium can move, because ultimately it's not a particle as it's traversing space. If it were a particle traversing space, it should be able to move faster than the speed of waves in the medium, right? Like a particle can move faster than sound, right here. A jet can move faster than the speed of sound. A whip can move faster than the speed of sound. So we can break the speed of sound. Why cannot we break the speed of light? So the answer is because when a particle moves through air, it moves as a particle. It's not bound by the speed of sound. It's not bound by the speed of waves in the medium. Unlike space, when a particle moves through space, it doesn't do it as a particle. It actually first converts into a wave. Only then is it moving through space as a wave. And that's why it's limited by the speed of light. And that also gives you the intuition, right? Because of this speed limit, you can intuit, you can feel already, oh, it must be a wave. It can't be a particle. As things are observed moving, they cannot be observed as solids. They must be observed as waves. So any motion of anything must be observed as a wave. It has nothing to do with the act of observation. It has to do, it does it? I guess, I guess it's the act of observation. Yeah, I kept saying it and I didn't even pay attention. So notice that quantum mechanics and relativity have the same issue of observation. Observation is at the key. So the whole field of relativity and quantum mechanics are the same field. It's the same project. It's the same universe. Like some people say, "Oh, we need to combine relativity with the quantum mechanics. We don't know how to do it." I'm like, nonsense. I keep coming back every time I think about relativity. Every time I think about either special or general relativity, it's always at the quantum level. I mean, electromagnetic waves are at the heart of relativity. The speed of light is an electromagnetic wave, and it's at the heart of special relativity, and it is a quantum effect. You have to think about what's going on at the quantum level. It's completely intermingled. It's one and the same. Oh my god. Anyway, I got this off my chest because I just came to this realization moments before I went live. Unbelievable. This has been on my mind for, I mean, I couldn't figure out the double slit experiment for years. This was bothering me. I couldn't figure it out, but now the puzzle pieces fit. This is I'm happy with this explanation. I feel that, right, according to my proposition 90, which I define what a proper proposition is, which is a proper scientific theory, I think this is a proper scientific theory because it's mechanical. I'm giving you a completely mechanical explanation, a simple mechanical explanation. I'm giving you a model of the experiment. I'm taking the experiment and I've modeled it with a mechanical contraption, with a 3D mechanical contraption. And I've peeled the onion of lack of knowledge one layer, at least one layer, maybe even more at a time. So it's a good scientific theory. Hey, ex Caracalla, what's going on? So I'm happy with this as a good scientific theory. This is, I mean, I've had breakthroughs before, but I think this is a major breakthrough. This explains so much. I mean, this goes to the heart. I saw a letter that Einstein wrote at the end of his days or whatever, and he said, "I'm still baffled by a photon. I still don't know what that thing is." And he had second thoughts about. I read that he had second thoughts about general relativity and special relativity that he didn't really. But so of course it's been 100 years. It's not fair that we would judge him. So we've had 100 years to think and rethink what's going on. So in the last couple of days, I've been able to prove GR directly from Newton and then GR directly from Galileo, and and I've been rethinking quantum mechanics again and again and again, and that's it. At least a double slit experiment, I have it completely explained mechanically, and it's so beautiful that I'm using E equals mc squared. This is like I still don't know how to derive it. I'm going from first principles. I'm taking it as a first principle. I'm assuming it's true. The conversion from energy to mass. I mean, it makes sense that, I mean, ultimately, okay, I'll rethink it. But assuming E equals mc squared, right? This is the only principle I'm relying on, right? What other principles am I assuming? I'm assuming E equals mc squared is true. I'm assuming the experiment was conducted properly. Of course, I never replicated this experiment, unfortunately. I should do that. But I'm assuming, right? I'm assuming that the experiment was done properly. I'm assuming that, I don't know, a photon was observed and it's not some artifact of the protocol. So assuming that the energy that they measured for the detection is correct, that it is a photon, and assuming that the photoelectric effect is correct and photons are experimentally verified by Einstein. So we're making a bunch of assumptions. So assuming the question was posed correctly, and I'm assuming that it's 100-year-old, at least 100-year-old question. I think this is the first time that anyone has proposed a purely scientific, I don't want to say purely, but a valid scientific theory to explain this experiment, right? So this goes to the heart of the definition of science. So we noticed a phenomenon, namely the double slit experiment, and we cannot explain it. So that was the case. As far as I'm concerned, I could not explain it. I could never find anyone who could explain it. So we had a phenomenon. We couldn't explain it. The next step was to come up with a 3D, understandable, mechanical, either simulation or mechanical contraption So we came up with it. Here it is. I just went through it. Now the step, I need to be able to make a prediction. So what prediction can I make from this theory? Where is the revolution? I need to be able to make a prediction in order to validate this theory as a valid scientific theory. Wow, I didn't think that far. Oh, let me think about that. What is special about this explanation that no one has thought of before? Well, my explanation is that it's the traveling, it's the propagation of energy that must convert a photon into a wave. And when it stops, it goes back into being a particle. As it stops relative to the observation, right? It has to do with an observer because it's all about observation. Apparently, that is the um, that is what it's all about, right? It's nothing to do that. This is there's no objective truth. I mean, talk about there's no objective truth. The theory of relativity is as unobjective as can be. It's called relativity. It's all relative to the observer. So for some reason, it's not really a wave. It's just because I'm observing it relative to me it's a wave, so that's even more bizarre than I can imagine at this point. So it's not really a wave, it's relative to me that it's a wave. So I don't know what to say about that. I don't have right now a prediction offhand. I don't have to come up with a prediction, so anyone can now build on top of this, on my work, on my theory. Anyone can build on this theory and come up with a prediction. And based on this prediction, come up with an experiment. Based on the experiment, actually perform the experiment, take, get the data from the experiment, compare to the expected. Is result close enough to expected? And validate my theory. So obviously, I'm sitting on the shoulders of of giants. All right, I got nothing more to say. This is completely overwhelming. This is too beautiful. If this is true, if we can validate this, um, I'd be very surprised. If this could be validated, I'd be very surprised. But look, it's even until then. Look, it's a possible explanation. It's a good explanation. It's completely scientific. There's no conspiracy theories here. There's nothing unscientific. I'm not saying anything unscientific. I understand general relativity, special relativity, more or less. I'm be the first one to say I don't, I don't understand it completely. Obviously, I don't understand it completely. When I think about it, there's so many internal contradictions within special and general relativity and quantum mechanics that there's still many contradictions to work out. But I think this is at least one contradiction that I've worked out, at least a tiny, tiny, tiny bit. Well, hopefully somebody is gonna find this interesting, and guys, we'll see you next time. Right? I want to keep it short. Let me see how long have we been streaming. It's 33 minutes. It's good. It's a good thing. All right. I'm gonna stay in this room. Yeah, and I'm gonna cut the stream. Thank you everyone for joining us. Bye bye.